Good morning and welcome to NASA's Johnson Space Center for today's mission status briefing of the STS-134 Space Shuttle mission to the International Space Station. We'll start with some opening comments and then take questions from reporters. For our comments and updates today, we have the lead space station flight director of the mission, Derek Hausman. Seated next to Derek is Dr. Samuel Ting, the principal investigator of the Alpha Magnetic Spectrometer. And next to Dr. Ting is Mark Sestilli, the AMS program manager from NASA headquarters. So I'll turn it over to Derek.
Okay, thanks Kylie, and good morning to everyone. It's a pleasure to be here to talk to you after what was an amazing day in space. As everyone knows, the #1 objective on Flight Day 4 today was to get the Alpha Magnetic Spectrometer removed from the shuttle payload bay and installed on the space station. And I'm happy to report that activity was performed absolutely flawlessly by the crew. We used the space shuttle robotic arm to remove the payload remove AMS from the shuttle payload bay, maneuvered AMS to a pre-planned handoff position. At that point, we paused there, had the space station crew, actually the 134 crew on station using the station robotic arm, grapple the payload. We released it with the shuttle arm and then maneuvered it to its final home on the S3 truss. At that point, once the installation and the attachment was complete, we applied power and handed over the payload to Professor Ting and his team to start the initial activation and checkout. So just an amazing day. It was a rewarding thing to watch both the crews on orbit and the ground teams execute those activities today, which again went very, very smooth and very, very well. And it's just an honor for me and my team to be a part of that and to contribute in a small way to getting AMS to space station. And before I hand over to Professor Ting to talk about the details and what he's seen so far, I'll just look ahead to tomorrow. What the crew was doing on space station as I left the mission control was prepping for tomorrow's spacewalk, EVA-1, which will be the first spacewalk planned for the mission. And by this time, I expect that Drew Feustel and Greg Shamatoff will be buttoned up in the airlocks, starting the Campout in preparation for tomorrow's EVA. So we're looking forward to that as well. And with that, I'll hand over to Professor Ting.
Good morning. I'm Samuel Ting, the principal investigator of AMS experiment. Coming together with me today is Professor Stephen Scheel, the director of one of the best physics institutes in Germany, who made a tremendous contribution to the AMS experiment. And also Professor Andreas Cantin, former rector of one of the oldest universities in Europe, from Bologna. They also made an extremely important contribution to AMS. For us, for me and my wife, Susan, the day began at 1 a.m. We came to the control room and watched the incredible work, how they take AMS out and out of the shuttle, put on the space station. So this finished about 4 or 5 o'clock. And we did some small check, and then we turned our detector on. Let me remind you, the detector has 300,000 channels of electronics, 650 microprocessors, and the detector are aligned to 1/10 of the human hair. So we immediately check all the detector. Everything functioned properly. Not a single wire was broken. Not a single electronic channel was malfunctioning. And right away, we began to see enormous amount of data coming down. And so let me just show 2 events. One is a 20 billion electron volt electron passing through the detector From the top is the transition radiation detector, which gives out a signal when electron pass through. Transition radiation detector was built in Aachen under the leadership of Professor Scheel, and followed by two layers of counters built by Professor Cantin's group, and then followed by silicon detector, and then in the bottom, a rain image Cherenkov counter, and in the bottom you see a blue shade. These are the showers. It shows, you can see how clean these events are. Events are coming in thousands, by the thousands. And these are basically the first few minutes. We have many events, we choose to two. The second event is a 42 billion electron volt carbon nuclei. And there on the top, you see the red. That's the energy loss because carbon is so heavy, so you have a lot of energy loss. And then you see two blue things, also energy loss, large energy loss because carbon is heavy. And in the bottom, you see a ring in this ring image Cherenkov counter. And this shows the detector functions properly without any noticeable deformation whatsoever. And we're very pleased. It took us 17 years to build this thing. And so finally, for the duration of the space station, we will be there. Hopefully be 10 to 20 years. And we hope with this device, we will be able to really make an important contribution to our understanding of the origin of the universe, understanding of cosmos. I don't see any hindrance. We also checked the leak rate of our detector and found out there's no leak rate. What's in space actually is better than what we measured on the ground. So we can last for 30 years, the detector. And from now on, what we're going to do is we're going to spend a few days, check more carefully every one of the elements. We did one check, and we're going to check it again, and check it again. And after that, we're going to sit tight, collecting data, also learn how to work with Johnson Space Center, and so to learn how to communicate with NASA. And after that, we will return to Geneva, Switzerland, where we have our park, which now will be finished, I think, in a few days' time. Finished.
Okay. All right, my name is Mark Cecili. I'm the NASA AMS Program Manager and have been so for the last, since 1994. From a NASA agency perspective, this is a major historic day because in a very real sense, a science voyage of discovery into our galaxy and beyond has started today from the International Space Station. And certainly NASA takes great pride in its partnership with the U.S. Department of Energy, which has sponsored this international collaboration. We cannot say enough how proud we are in NASA to have a world-class science facility like this on the space station for 10 or more years. Certainly it was a challenge for NASA to fly this on the space shuttle and then on the space station. NASA had a very, very fine project team here at the Johnson Space Center, led by Trent Martin, my project manager, and Ken Bolwig, my deputy project manager, who are among the best engineers in the agency. And through their efforts, and the efforts of many other good people here at the Johnson Space Center and at the Kennedy Space Center, we were able to achieve what we did today, And I think that's all I want to say.
Thank you, gentlemen. We'll start with questions here at the Johnson Space Center. Seth?
Seth Borenstein, Associated Press. First, I have two, one for Dr. Ting. I know it's early, but you did get a good amount of results already. I assume none of them are surprising, but are all the results you're getting exactly what you would expect, or is there anything already a surprise?
In a few seconds, these are first few minute data. If I say there's something surprise, then there's something wrong with me. And we are going to do this very carefully, very systematically, because as I mentioned to you last time, in the next 30 to 40 years, I think it will be very difficult for anyone to make a spectrometer of this precision to space. And therefore, it is extremely important for my collaborators and I do things correctly.
And thank you. And for Derek, just looking ahead to the EVA today, you could look at it and say it's a very sort of routine EVA. Which are your, I know we went through this a while back, but can you go through what which of the sort of routine tasks are the most priorities, and which one are you more concerned about in terms of the ability to get done, or most worried that it can get done right?
Mm-hmm. Yeah, as you know, after all these years of success, we tend to make these things look routine and feel routine, but they never are. Of course, anytime you put the crew in a spacesuit and send them outside, there's risk involved, but we understand how to do that, and we do it well, and we manage the risk appropriately. But EVA-1, the first thing that we get to right out the door are the DoD MISSE payloads, which are going to be installed externally on the space station truss. We are retrieving a MISSE that was flown previously, and it's reached the end of its life, and it's going to be brought down to be studied, and we're deploying 2 additional MISSEs. In addition to that work, we are setting up for a top-off or a refill, if you will, of one of the cooling loops on the outside of the space station, one of the ammonia cooling loops. So, I won't say it's easy, but all the tasks are relatively straightforward. And although I worry about everything, there's nothing in particular on EVA-1 that I'm more worried about than the others. We did talk before, but on EVA-2, as the follow-on to the ammonia refill task, we actually actuate quick disconnects on lines that have ammonia, pressurized ammonia. And these are the quick disconnects that we've had challenges with in the past. We've had issues with them leaking and sticking and that sort of thing. So, looking ahead at all the EVAs, I would say that would be the area of most concern, would be the work with those ammonia QDs on EVA-2.
Clara Moskowitz with Space.com, and 2 questions for Dr. Ting. First, the 2 particles that you mentioned today, are those particles that instruments on the Earth can see, or are they only visible in space above the atmosphere by an instrument like AMS?
On Earth, you can produce these particles in accelerators, in man-made accelerators. But on Earth, you are not able to measure this particle from space because they will be absorbed by Earth's atmosphere. So to see the cosmic rays of this energy and this mass, you really have to go to space.
And my second question is, if there was no International Space Station, could there be an AMS? In other words, could the AMS exist free-floating in space?
As you know, in 2005, we were removed from the manifest. So we have looked very carefully whether there's a way we can put AMS in space. But because of the size, the precision, and the power required, and also the rate of data coming down, it's simply not possible to do it with a rocket unless you put the billions, and billions. You need a 2,500 watt of power, and you need a high rate data transmission. Okay, you need a large platform. Space station is an ideal place for this type of experiment. And only place.
Thank you, Mark Carreau, for Aviation Week. I had a couple questions, kind of housekeeping questions, really, but how soon after AMS was anchored to the space station did you start to see this flow of particles through the detector?
First, we check there's no leak rate, nothing leaked. I think within hours, a couple hours, 2 or 3 hours.
Thank you. Another housekeeping question, if you can address this. What's the size of your AMS cadre in Houston, and how soon will you migrate to CERN for the long haul?
We have collaborators total in Houston about 60 people, and we will not migrate to CERN. We'll return to CERN. Return to Europe, I should say.
And when would you anticipate that would be?
Our building, we build a new park, will be finished by June 15th. And because there was a shuttle delay, originally was the 29th, then May 16th, we hope we will return as early as possible, even though we're aiming at June 15th, and I think by end of June we will be gone.
Thank you, sir.
Yeah. What we want to do is when we leave, we have a good working relationship with Johnson Space Center, so we don't have to come back again.
Any more questions here?
Seth Bornstein, again, one more for Dr. Ting. Since we're approaching the last shuttle flight after this, a lot has been talked about of, sort of the legacy of the shuttle. And many people say the legacy of the shuttle is not so much the shuttle itself, but things like Hubble and they hope AMS too. And since you said space station's the only place you could have put this, mm-hmm. and I assume shuttle's the only way you could have gotten, mm-hmm. you couldn't have used any of the other transportation methods. Mm-hmm. I was wondering if you minded telling me a bit about how important the shuttle program is for you, especially since you've been one of the few who's mm-hmm. been on it, kicked off of it, mm-hmm. and back on, mm-hmm. Sort of the importance of the legacy of the shuttle to you.
Without the shuttle, I think it would not be possible to do an experiment of this precision, right? And for a duration of 20 years, and collect terabytes of data, measure energies to trillion electron volt. You simply, at least I would not know how to do it, and I think my collaborators will share this opinion.
Thank you. We'll take questions from the phone bridge now. We have Marcia Dunn, please.
Yes, hi, can you hear me?
Yes, we can.
Yes, Dr. Ting, I'm wondering how soon after the installation of the spectrometer or the detector is all turned on? Was that in a matter of minutes or a little longer?
When we were plugged in, when we were connected electrically with the space station, and within an hour, we were checking all the things. And so within hours, we were collecting data. This was early in the morning, and I was slightly sleepy, so I couldn't tell you it's 5 o'clock or 6 o'clock. But it was very quick. We had no problem whatsoever.
Thank you. And did I understand you to say earlier that already you have registered thousands of particles passing through your device?
We have thousands and thousands of signatures already.
Thank you. That's all. Thank you very much.
Okay. Next on the line is Irene Klotz.
Hi, I'm Irene Klotz with Reuters. Can you hear me?
Yes, we can. Irene, are you still there?
Yes, can you hear me okay?
Yes.
Hi, thanks very much. I have a couple questions. For Mr. Sestilli, is there still going to be NASA budget for AMS support? Is there anything that NASA needs to pay to, like, the ISS program as a user?
The major part of the AMS budget we clearly spent getting ready for this launch. We have a much smaller budget plan for the post-launch time period to provide operational support to Professor's team here in Houston as well as at CERN. But it's considerably smaller than what we've been spending to date. We spent to date since 1999 about $85 million on AMS unique costs as far as integrating on the shuttle and the space station leading up to today. Beyond this day, our costs through the next several years will probably be on the order of perhaps another $10 million. So it's much smaller.
Thanks very much. And for Professor Ting, I'm sorry if I missed this, but is there also a calibration period that AMS will need to go through before you would say that it's in its kind of full research mode?
So far, the data we have seen is based on the calibration we have done underground. It shows all the detectors are functioning. We have built-in alignment system and built-in calibration. We will constantly self-calibrating the detector all the time.
Okay, thank you. And could you maybe just describe a little bit about what happens with the AMS data? Where does it go once it's relayed, like through the TDRS satellite and through the NASA system? Is it going to, like, individual science team member institutions, or does everything go first to CERN and is parceled out from there?
The data will come to Marshall, and then now comes to Johnson Space Center. After end of June, it will go to CERN, and from CERN, it will go to all the collaborating institutes for analysis.
Thanks. And my last question for you is this has been quite a roller coaster ride since AMS 01 was first unveiled. And if you could maybe just talk a little bit about what sort of, if you had a sense of relief to see it up, finally up on station, was it worth all the headaches and what it took for you to keep this team together, form the team, keep it together, and reach this day? Thank you.
I don't have headaches, but unfortunately, my wife sometimes has headaches. And whether it's worth it or not, it's hard to say. All I can say is we enter into a region nobody has entered before. What we're going to see, nobody knows. So we explore an unknown region. So whatever we see, because of the precision, because of the energy we reached, it certainly will contribute to a better understanding of the cosmos.
Okay, next on the line is James Dean.
Thank you. This is James Dean from Florida today with a question for Derek and a couple for Dr. Ting. First, Derek, I just wondered if you might have any updates on the status of the TPS analysis?
I do not. My focus over the last 10 or 12 hours has been Flight Day 4 and AMS install and the events that followed that in the timeline. I believe you have a briefing later today from Leroy Kane, and I expect that he'll have the latest on the TPS analysis.
Okay, thanks. Dr. Ting mentioned to the crew in your remarks that this had been a difficult experiment. Why has it been so difficult, and what has been the most difficult part? Has it been the technology or the political aspect of it?
It's hard to compare apples with oranges. And, certainly we have tried the best to build the most precise detector we can accomplish. And the transition radiation detector that was built under Professor Shell, we have done in such a way the leak rate is 5 micrograms per second. And there are 2 meters long tubes and filled with xenon and CO2. CO2, of course, is extremely difficult to contain. That's why Coca-Cola never lasts for a long time. But the people in Aachen were able to build this detector such that the detector would stay active for 30 years. And the detector built in Bologna under Professor Cantin with multi-redundancy and measured the time to 160 picoseconds. And these are really, what we try to do is to the limit of abilities people normally do in accelerators. And we try to keep that precision, but do it in space.
And I just wanted to ask, I'm afraid I might be mischaracterizing something you said earlier, but you described how, I believe you said that trying to find antimatter would be like picking a single drop out of a rainstorm, a single drop of a different color. Is that in general the process of facing you for finding the most difficult things, dark matter, antimatter? Is it a 1 in billion sort of chance of finding those things, or is that not really the right reflection of how difficult it is to find these things?
Okay. 1 in a billion means you have multi-redundancy, you have self-calibration, and the important thing is always know how your detector behave. In my youth, I have done 2 or 3 similar experiments, including the one I was awarded the Nobel Prize, and that was a really also difficult experiment, but nothing compared to the experiment we're doing now. The difference is experimenting accelerators. If something goes wrong, you can go to fix it, or if you don't want to, you can send a student. But in space, you can send nobody. And so this detector, AMS, has many redundancies and many self-checking, and to make sure everything behaves properly. To keep it for 20 years is really not an easy thing to do.
Okay, next on the line is Bill Harwood.
Yes, thanks. I've got one for Professor Ting, if I could. The one question I get asked, Professor, frequently about AMS, aside from the science, is what makes something like this cost as much as it did? And I realize that you could talk for days about how that breakdown works, but is there some way to tell the average reader why a machine like this cost $2 billion to build, to test, to get up into space? Thanks.
Why, I do not know. The calculation of cost in a large international collaboration spending across the globe is not exactly easy. We have people from the Far East, people in Europe, people in Mexico, people in the United States. The labor costs are not exactly the same for different countries. And so to estimate this is way beyond my ability. And in January 2005, NASA made an estimate based on the available people and the laboratory we have to specially build, and the test equipment we have to build, the new buildings we have to build, and material we have bought, and how many professors, how many students, how many technicians, add them up in NASA's way of counting. And this is how we gradually approach this number.
Thanks. And if I could ask one more, you've mentioned frequently whenever you talk about AMS that no physicist worth his salt will make a prediction about what something might find, and you've always stressed that it's the unknown that you're really looking forward to. Can you elaborate just a little bit on the unknowns? I know you don't know what you're going to see, but I mean the excitement of going after something that no one's ever looked at before with an instrument of the precision that you guys have built. Just your general mood going into this because of the chance to see something new. Thank you.
Well, it's really rather difficult for me to answer this philosophical question. I only want to mention, if you look at the history of accelerators in the United States and in Europe, in the 60s, the highest energy accelerator were built at CERN and built at Brookhaven, and their original purpose was to study nuclear force. And what was discovered was a new type of quarks, break down fundamental symmetry, neutral currents. That's in the 60s. In the 70s, a very large accelerator was built in the United States, in Fermi National Laboratory. The original purpose was to study something called neutrino physics. What was discovered was the fifth and sixth type of quarks. In Stanford, in 1970s, United States built a very powerful electron-positron collider. The original purpose was to study the quantum property of electricity. What was discovered was the fourth quark, the third type of electrons, and particles inside the protons. So when you build something new, you ask the best physicists to tell you what you can see. But the best physicists, of course, base their judgment on existing knowledge. Discovery of something new is go beyond the existing knowledge. That's why it's difficult to predict. Just to confirm somebody's theory is really not that interesting. It is go beyond the theory. That's how science advances.
Okay, that must be all on the line. Are there any follow-ups here?
Clara Moskowitz, again for Space.com. And this is a question for both of you, AMS scientists and project manager. If you could talk about just this morning your emotions while the robotic operations were going on. I understand that it was somewhat complicated, and did you have any anxiety over how that would turn out?
For me, none. But my European collaborators were up all night watching them. I have no doubt they will be successful because I've talked to them quite a few times.
Well, for myself, like Professor said earlier, we were all very tired, but I think we marveled at the precision at the way everything went. After all the years of doing engineering and things going wrong or being tough or whatever, when it finally came time to install in the space station, it just went very, very well. It really did. As Professor Ting said a moment ago, when it came time to activate the AMS, we were activating within hours and no major incidents. All the detectors came up. So a feeling, being happy about it, seeing it's finally starting to work. When we started looking at these particle tracks a few hours ago, It's very, very impressive. It's terrific science, and it's making it all very much really worthwhile.
Let me just add to what Mr. Sestelli said. We had no major issue, also no minor issue, no issue whatsoever.
Okay, any other follow-ups? Seeing none, we'll go ahead and conclude this briefing with a few programming notes. Coming up at 2 p.m. Central Time will be the video file, which shows a compilation of newsworthy items from across the agency. At 3 p.m., that briefing that will follow the mission management team meeting will air on NASA television. And at 4 p.m., we'll begin showing the video highlights from Flight Day 4. So with that, we'll send it back to Mission Control as the crew members wrap up their day in space. Thank you.